Hi folks, this is Calc 3, Checkpoint Quiz 3. We're asked to state the epsilon-delta definition of limit. So remember what this means. This means that we can get the output of the function r of t as close as we want to the vector L by guaranteeing that the t's are close enough to t naught without t actually having to be at t naught. So as usual, we're going to let epsilon be our tolerance for how close the function is to the target L, and delta is going to be how close we need to get t to be to t naught. So given epsilon greater than 0, there exists delta greater than 0, so that if 0 is less than the absolute value of t minus t naught is less than delta, then the magnitude of the difference r of t minus L is less than epsilon. So a couple of notes here. Remember, from this is the reason why this is here is the same reason as from Calc 1. I need t to be close to t naught. How close? Within delta units of t naught, but t doesn't necessarily have to be equal to t naught, which is why the 0 is there. Also, too, remember the outputs and the limit itself are vectors. And so we can show two vectors are close to each other by showing that the magnitude of the difference is small. So if we want to think about this, let's say L is our target vector, and we've got r of t. Then the difference, r of t minus L, is going to be this vector here, the vector that starts at the terminal point of L and goes to the terminal point of r of t. So this is the difference, r of t minus L. And so what I'm saying is that if I look at the length of this vector getting really small is the same as the vector itself going to 0, which is the same as r of t getting close to L. And so that'll do it for number 1. Okay, in number 2, we're given a vector-valued function, and hopefully we recognize this as being a helix. We've got a sine of an angle and a cosine of an angle in two of the components. That means in the xz direction we have circular motion. The t in the y component is going to drag that circle out along the y-axis. So it's going to create one of these spirals again, going like this. So that's how we can visualize this curve. And we're asked to find the tangential component and the normal component of acceleration and check that this equation works. Now there are lots of different formulas for AT and AN, and you need to be fluent in at least a couple of them. Depending on the situation, one of these could be easier than the other to get. So let's start off with AT, the tangential component of acceleration. That's the acceleration in the direction you're going. So as we talked about in class, not surprisingly, it's the derivative of the speed. So in order to get the speed, we first need to find the velocity. And as you recall, the velocity is the first derivative of the position function. And so we get the derivative of sine of 2t, 2 cosine 2t. The derivative of t is 1. The derivative of cosine of 2t is negative 2 sine of 2t. And so then to get the speed, we square the components, add them up, and take the square root. So I square 2 cosine 2t, I get 4 cosine squared 2t, plus I square 1 and get 1, plus I square negative 2 sine of 2t, and I get 4 sine squared 2t, and that's all going to be underneath the square root. I have 4 cosine squared of an angle plus 4 sine squared of that angle. And so Pythagorean magic kicks in. I'm just going to get 4 from that sum, but I still have the 1 from before. And so I get the speed is the square root of 5. So as we've seen in many of these helix problems, we get a constant speed, which means that our AT then, which is the derivative of that, is going to be 0. So in this helix, there's no acceleration in the tangential direction, so all the acceleration must be in the normal direction. Okay, so to find the acceleration in the normal direction, once again, we have a couple different formulas to look for, or to look at, to consider. The one I'm going to use is this one. A sub n is the square root of the magnitude of the acceleration squared minus a sub t squared. So to use this formula, I'm going to look at the acceleration. The acceleration is the derivative of the velocity, and that's the second derivative in turn of the position function. So remember what our velocity was. It was 2 cosine 2t, comma 1, comma negative 2 sine of 2t. That's going to give us our acceleration a of t is negative 4 sine of 2t, 0, negative 4 cosine 2t. So we get the magnitude of the acceleration then is, I'm going to square these and add them up. Negative 4 sine of 2t squared gives me 16 sine squared of 2t. 0 squared is 0. Negative 4 cosine of 2t, square that, 16 cosine squared 2t. We'll take the square root of that. And as before, we have some Pythagorean magic happen. 16 sine squared of 2t plus 16 cosine squared of 2t. That's just going to be 16. The square root of 16 is 4. So I stuff this in to get a sub n is the square root of the magnitude of a squared is 16 minus the tangential component of acceleration worked out to be 0, and so I get 4. So once again, since there's no tangential component of acceleration, it makes perfect sense then that all the acceleration has to be in the normal direction. And since the magnitude of the acceleration is 4, then the magnitude of the normal component also has to be 4. So that checks out.